speaker is Anastasia Isychev from TU Wien. She's going to talk to us about mixed precision tuning.
Okay, thank you. Thank you so much. I haven't even started yet. All right, so today I'm going to talk about the cost of soundness in mixed precision tuning, but first let me clarify what mixed precision tuning is. So it is a performance optimization designed specifically for numerical programs, and what it does, it assigns potentially different finite precision types to variables and arithmetic operations. And it is based on the observation that operations performed with fewer bits in low precision are generally faster than the same operations performed in higher precision, but they have lower accuracy. And secondly, different operations inside one expression contribute differently to the overall accuracy of this expression. So what the tuner needs to do, it has to navigate the accuracy performance trade-off, and unfortunately, all the potential precision assignments it's not a smooth function. So there might be jumps in accuracy and in performance. So what the tuner is trying to do, it is trying to assign the lowest possible precision assignment that satisfies some user-defined accuracy constraint. Let me show you an example. Say you have an algorithm. The details of the algorithm here are not important, but say you want to implement it accurate up to 10 to the power of minus 16. So as a developer, what are your options? You could use very high precision, say 128 bits or quad precision, and assign it uniformly to all operations, and then executing such a small code snippet on 1 million samples would already take 5 seconds. But of course, it satisfies your accuracy constraint. Actually, it overly satisfies it, overshoots it by 18 orders of magnitude. So if this is too slow for you and too accurate, what can you do? If you just have uniform precision assignment, you can go to 64 bits or double floating point, and then such a code snippet, again on the 1 million samples, would run much faster. It's way under 1 second, but it doesn't satisfy the accuracy constraint that you had initially. So what can you do? What mixed precision tuning would do is you can keep all of the operations in high precision except one and downgrade it to double floating point precision. And such an implementation would satisfy the accuracy constraint and actually quite closely. And also it would run 10% faster than the original uniform quad precision. So this is just to give you an idea what this optimization is doing. And the tuners that do such optimizations can be classified in two big conceptually different groups that differ based on how they estimate accuracy of the generated programs. And on one side, you have sound static tuners that use sound static analysis to compute the worst case rounding errors of a program. And they provide guarantees because they talk about worst case scenario, but because of that, they are also overly conservative. On the other side of the spectrum, we have dynamic tuners that use sampled values to reason about rounding errors. And because of that, they do not provide any guarantees since they are not sampling all possible values. But this also enables them to be more aggressive in the way they are optimizing the programs, which potentially might be beneficial. And there are multiple tools in each of the groups, and there are comparisons and evaluations within each of the groups. But the question remains, how do these two conceptually different groups of tuners compare? And the hypothesis is that sound static optimizers are inherently slower and less effective than the unsound dynamic ones. The question we wanted to ask is by how much exactly? So if the user wants soundness guarantees, basically what is the cost attached to such a choice? And how to answer this question? First, we needed to find the common ground on which both types of tools can be evaluated. So we have reference points for direct comparison. And we needed to find a meaningful metric that will quantify effectiveness of the tuners. So for common ground, we started off with the FE-bench standard benchmark set that is generally used for assessing quality of numerical analyzers and optimizers. But some of these benchmarks actually contain loops and conditionals, and currently none of the static tuners can handle such control flow constraints, control flow statements, without any pre-processing. So there would be no reference point for static tools, which is why we had to exclude them, and we only compare on the straight line code. And another important point, as a part of the specification, we have these accuracy constraints, and the effectiveness of the optimization also depends on this part of the specification. It was previously shown that the most effective optimization can be done if the constraint, if this error budget, is just below what the uniform precision can provide. So we came up with 3 different scaling factors, and we took as a reference value what the analyzers, the tuners, reported for uniform double precision for each benchmark, and then we scaled it down to obtain different specifications. For effectiveness, we essentially needed the metric that would tell us how well the tuner can navigate this accuracy-performance trade-off. And because we are comparing sound and unsound tools, we called this metric cost of soundness. And it has multiple components. For each optimized program, we first evaluate the performance improvement in terms of speed up in running time of the optimized program P prime compared to the original high precision program P. For accuracy, it was a little bit more tricky because just comparing the difference of the accuracy, the increase of the error, is not meaningful because it varies a lot across different benchmarks. And additionally, conceptually, the tools, these 2 different groups of tools, optimize with respect to different reference implementations. So sound tuners optimize with respect to real valued ideal implementation that doesn't have any error in it. And dynamic tools usually run some kind of high precision implementation and use that as a reference to optimize further. So as the accuracy metric, instead of just computing the increase of the error, we are assessing how well the tuner can use the allocated budget of the error. So basically within the budget that we, or the user, gave to the tuner, how much of this budget is used in order to improve performance. And we combine these 2 metrics into this cost of soundness combined metric, where we give higher weight for performance because mixed precision tuning is a performance optimization, and we normalize this use of budget to essentially equally punish the programs that violate accuracy constraints, so they overshoot the budget, and the ones that do not use the budget at all. And for this comparison, we focused only on the tuners that operate on floating point precisions, either IEEE or arbitrary ones. And among those that were available open source, there were 2 standalone static tools, FPTuner and DAISY, and the meta optimization Regina that can be combined with any static tool. So for dynamic tuners, there were only standalone tools, and we compare with them. I will show you results only for one of the error budgets, but actually results look similar. The trends are similar for other budgets as well. So what's going on this graph? Here on the x-axis, we have the 100 benchmarks sorted. And on the y-axis, I have this abstract cost of soundness metric that I explained to you. So higher values here mean better. So basically, the red curve of the triangles is the best, most effective tuner. And I don't know how well you can see the size of the font, but actually the most effective tuner is the combination of a sound tuner with regime inference. So what regime inference is, in a nutshell, it subdivides the input space for a program into multiple subdomains and optimizes each of these subdomains separately. So what this result actually tells us is that the soundness does not inherently come with a cost. And if you enhance sound tools, sound optimizers, with some additional algorithms like regime inference, you can, without sacrificing accuracy guarantees, you can also outperform dynamic tuners. For standalone tools, the picture was slightly different, and as expected, they were, in fact, static tools were in fact much less effective than dynamic ones, and there was also a pronounced drop in effectiveness when we decreased the error budget. For dynamic tuners, we also observed this drop in effectiveness, but it was not as steep across different targets, and it happened mostly because the optimized programs violated the accuracy constraints more often and on more benchmarks. In terms of optimization time, there was a clear winner that optimized programs way below half of a second, and there was the slowest technique that was a combination of this regime inference that repeatedly calls sound tuners on different parts of the input space. But otherwise, we were surprised to see that there was no clear trend that sound tuners were either slower or faster than the dynamic ones. So let's revisit our hypothesis. We now know that, in fact, sound tuners are not inherently slower than the dynamic ones, and they are less effective if we are talking about the standalone tools, but recent developments in meta-optimizations allow sound tools to compete and actually be more effective than dynamic ones. So what I would like you to remember from this talk is that the goal of the study was to quantify the difference in effectiveness between sound static and unsound dynamic mixed precision tuners. And on simple programs, we concluded that soundness does not inherently come with the cost, which was a pretty pleasing result for us. But of course, there is a caveat that on complex programs that contain control flow, dynamic tuners remain, for now, the only choice. So this result, we don't know yet if it will generalize. The static tools are not there yet. Thank you for your attention.
In machine learning, you do very different type of lot more small precision parts, and also things, even though there's loops, they can be a lot more statically countable. So can you apply some of these techniques to like machine learning kernels?
I mean, that depends, of course, on what kind of loops, right? So say if in embedded systems, they also use a lot of these loops, but if you read a fresh set of values every time, and there is no rounding error that would propagate from iteration to iteration, then it's the same as if you don't have a loop. So for this scenario, for sure, you can apply it as is. And for other scenarios, you can try dynamic ones, but then, again, the accuracy guarantees are out of the window.
Thank you for the talk. I wonder how we can use your method to get a scheme, a quantization scheme efficiently, more efficient quantization scheme. Did you think about that? You compare methods, but yes. Can you create methods?
Well, that was not the goal of this particular study. Of course, there are different, so there is research in this area, yes. That was not the goal of this study.
Okay, so you see that, you can see that your approach can be, for example, integrated in some training method for neural network or something like that, to make a quantization more efficient after that.
Yes, for sure. That, I mean, I wouldn't be able to name the papers on the top of my head, but yes, people apply mixed precision tuning in context of machine learning as well.
Okay, thank you.
Thank you.